Okay, my name is Suraj Jami, 18BEC0281. Serial number is 18. Suraj.jami 2018 at the rate of vitstudent.ac.in is my email ID of VIT University. So today I'm going to explain digital assignment 2 of computer organization and architecture. So, so for first we have to choose a research paper. So let's go to the research paper I have chosen. Okay, okay, this is the research paper. Analysis of high performance floating point arithmetic on FPGAs by some authors. Okay, let's go to the first question. Okay, so the first question is explain how the selected paper is related to the COS syllabus or curriculum. When we have to represent very small or very large numbers, a fixed point representation will not do. The accuracy will be lost, therefore we will have to look at floating point representations where the binary digit is assumed to be floating. When you consider a decimal number 12.34 star 107, this can be also treated as 0.1234 star 107, where 0.1234 is the fixed point mantissa. The other part represents the exponent value and indicates that the actual position of the binary point is 9 positions to the right, left of the indicated binary point in the fraction. Since the binary point can be moved to any position and the exponent value adjusted appropriately, it is called a floating point representation. The recent FPGA devices have multi-million gate logic fabrics capable of achieving frequencies up to 300 MHz, that is 10 to the power 6, reasonably large on-chip memory and fast I/O resources, power of chip communication to either processors or memory. By convention, you generally go in for a normalized representation wherein the floating point is placed to the right of the first non-zero significant digit. The base need not to be specified explicitly, and the sign, the significant digits, and the signed exponent constitute the representation. Also, it's important to know that the processors require multi-layered processing pipelines so as to perform floating point arithmetic calculations. Pipeline architectures for search kernels can use deeply pipeline floating point units to achieve an order of performance more than the general purpose floating point processors. Okay, so let's go to the next question. Draw the existing architectures discussed in the paper using appropriate raster graphics editor software in encapsulated PostScript file format, that's EPS. Okay, so the below diagram has been taken from the research paper, which shows the basic block diagram of the existing architecture of GPA design. This was directly from the research paper. I have gone through the research paper like couple of times so that I can answer these questions very easily. Okay, there are so many blocks for the execution of the program. So the first, this one is adder or subtractor, and the second is multiplier. Okay, for the adder or subtractor, we need a exponent comparator, denom, mantissa swapper, exponent subtractor, shifter, mantissa adder, normalizer, and rounding. Okay, so then multiplier consists of exponent adder, denom, mantissa multiplier. For this mantissa swapper was there, and this one mantissa multiplier. So yeah, let's and normalizing and rounding. So it's a bit difference for these two. Okay, so let's go to this thing. Draw the tabulated results and graphs using Office Suite in EPS file format. Okay, so this table was made with Microsoft Excel. Okay, so the table one shows the analysis of 32, 48, 64-bit floating point adders. So we have some parameters so that we can compare these parameters according to millimeter, maximum, optimum, everything. So yeah, precision is 32, 48, 64-bit, and number of pipeline stages, area, LUTs, flip-flops, clock rate in megahertz, frequency or area in megahertz or slice. Okay, So according to these values, we had to create a graph of frequency by area versus number of pipeline stages for multipliers. So these bold square dots are for 32-bit, and this light cross mark dots are for 48-bit, and these bold circle dots are for 64-bit. Okay, so this was the graph possible due to that table, and this one is the, let's go to the next question, that's fourth one. Draw the proposed architectures discussed in the paper using diagramming and vector graphics application software in EPS file format. Okay, so okay, this is the thing. Okay, so we have input registers and then pre-adder, pipeline registers, memory, systolic registers, feedback registers, and output registers. These all blocks constitute together to form the proposed architecture discussed in the paper. Okay, so we have these things. Okay, so this is okay. Let's go to the fifth question right now. Draw the transistor level internal diagrams using the electronic schematic capture and simulation tools in EPS file format. So we have this transistor level internal diagram where the first block is decomposed. There is operation 1, operation 2, and then expect effective exponent and exponent differential calculator. The outputs from the compose come to there, and then there is swap between these two. Then we have significant shifter that goes to the TZD, then to the sticky bit scale. From the significant shifter, comes to the binary adder comes subtractor. From the EOP calculation, it also comes to the binary adder subtractor, and the swap also goes to the same. Then these goes to the shift calculation, LZD, and normalization. That normalization thing is goes to exponent adjust, rounding. The exponent adjust thing once again goes so that we can have the exponent final, and the final block is compose, which gives us output data and all the exception signals. Okay, so the sixth question is, compare the proposed architectures with the existing architectures in your reference books. We can compare the aforesaid multiplier designs in terms of delay and power, and thereafter proposes a new design using carry look ahead adder. Using the classic timing analyzer tool, it was observed that the new multiplier design using carry look ahead adder has less delay compared to the other multiplier designs. The power consumptions the power consumption calculations of the multipliers were done successfully using Power Analyzer tool. It was observed that the power consumption of all the multiplier designs were more or less the same. So let's go to the next question. It's it's list the advantage of the proposed design over the existing design. Okay, so okay, using the proposed design, a Silnix Vertex 2 Pro's XC2V125 device is able to achieve 19.6 gigaflops for 32-bit matrix multiplication. This is a 6x improvement over the 2.5 GHz Palladium 4 processor and 3 times improvement over the 1.25 GHz G4 processor. Okay, domain specific modeling is a hybrid top down plus bottom up approach to performance modeling that allows the designer to rapidly evaluate the candidate algorithms and architectures in order to determine the design that best meets criteria such as energy, latency, and area. FPGA-based floating point architectures like the matrix multiplication employing efficient floating point units can achieve a significant improvement in the performance over that of the processors. Okay, So let's go to the next question. List the merits and demerits of the proposed and existing techniques or hardware. Okay, so the first point is time delay can be reduced. The second is power consumption is optimized. The next one, the proposed design improves the speed. It calculates one or more carry bits before the sum. This reduces the wait time to calculate the result of the bits which have a larger value. The carry logic block becomes very complicated for more than 4 bits. The problem size should be greater than the sum of the adder and the multiplier latencies. Okay, these are the merits and the demerits. So let's go to the next question. That's ninth one. List the application of the proposed design. The fused floating point add subtract unit is used mainly in the application of digital signal processing. The main application is in fast Fourier transform and discrete cosine transforms. Butterfly operation R of FFT are benefited with the help of fused FPU in terms of low power consumption. The domain-specific modeling is a hybrid top-down plus bottom-up approach to performance modeling that allows the designer to rapidly evaluate the candidate algorithms and architectures in order to determine the design that best meets the criteria such as energy, latency, and area. Use of this architecture to design a domain-specific hybrid FPGA for various floating point computations. High performance and scientific computing applications are typically compute intensive and require high throughput rates. Examples of such applications are radar, sonar signal processing, image processing, molecular analysis, etc. Okay, let's go to the last question of the digital assignment. Uh, Draw the flowchart or algorithm of transistor level circuit proposed in the design in EPS file format. So the design used is shift adder multiplication algorithm. So first A and B and are read, then it is initialized with E equal to 0, A equal to 1, I equal to 0. Then it goes to E star AI. Then if it's 0 1, it goes to C equal to C plus B. If it's 10, it goes to C equal to C plus minus B. Then if it's 1 0 or 1 1, it directly goes to arithmetic shift right of C E equal to AI. Then it goes to I equal to I plus 1. Then it goes to I equal to N. Okay, then the product is equal to C. So this is a basic flow chart for shift arrow multiplication algorithm, which was possible by drawing with draw.io. So okay, thank you. This was my time. Thanks.